curious observant. Looking at this 3D render, you're seeing a physical contradiction. On the left is a modern Kirin processor, patterned with features equivalent to 5 nanometers. On the right is the machine that supposedly built it, an older generation ASML scanner. According to the standard physics of semiconductor manufacturing, what you are looking at is impossible. A machine built to project light at 193 nanometer wavelength shouldn't be able to carve silicon features a fraction of that size. For years, the entire global computing ecosystem relied on singular choke points to advance. If you wanted to build frontier silicon, you needed Extreme Ultraviolet, or EUV scanners from ASML. If you wanted to run a smartphone, you built on top of massive monolithic operating systems like Linux and Android. When a massive multinational corporation is suddenly severed from those foundational tools, the result is usually immediate operational collapse. Factories completely halt, yield drops to zero, and software pipelines run dry. But Huawei survived by engineering a completely independent, parallel computing ecosystem, building it from the atomic level of the silicon straight up to the software architecture. This image captures the physical environment where these engineering workarounds happen. Inside these sterile cleanrooms, workers operate advanced manufacturing equipment under strict operational limits. The primary physical constraint they face is light. They are denied access to extreme ultraviolet light, which has a wavelength of 13.5 nanometers, the metric thought necessary for carving advanced transistor geometries. Without EUV, engineers must fall back on deep ultraviolet immersion, or DUVI. This involves using older scanners that project light at a much wider, comparatively clumsy 193 nanometer wavelength. By forcing 193 nanometer light through purified water, it refracts, focusing on an ultra-fine point. Using self-aligned quadruple patterning, the silicon is exposed 4 times, layering patterns tightly to create dense lines. If any pass misaligns by a fraction, compounding errors cause the structure to collapse. Producing these early sovereign chips is a brutal, heavily subsidized war of attrition against the physical limits of light refraction and low silicon yield rates. This photograph shows the exterior of a SMIC fabrication facility, the manufacturing partner tasked with scaling these heavily constrained non-EUV designs. Because true front-end geometric transistor shrinking is practically blocked without EUV, engineers must rely on design technology co-optimization, tweaking layout and standard cell design to squeeze out performance. Instead of building wider, they build vertically. 2 flat silicon logic dies physically stack on top of one another, instantly fusing their pathways together. Notice in this thermal diagram what happens to a vertically stacked chip. Fusing active logic dies directly together creates a severe penalty, trapping extreme heat directly in the center layer where it cannot escape into traditional heat sinks. The inability to shrink transistors forces a strict engineering trade-off. By bypassing the 2D density limit, you inherit an extremely complex 3D thermal management challenge. Looking closely at this smartphone screen, the Harmony OS Next logo acts as the consumer-facing interface that masks this incredibly complex hardware engineering. To achieve true software sovereignty, engineers had to remove millions of lines of legacy code from the Android open source project and the massive monolithic Linux kernel. This schematic compares the massive monolithic Linux block to the tiny HongMeng microkernel. Microkernels historically suffer from high latency due to fragmented data pathways. To fix this, HongMeng utilizes service coalescing, merging fragmented external pathways into thick, high-speed pipelines to accelerate data flow. Keeping the microkernel's footprint tiny provides a massive security advantage. It enables formal mathematical verification, eliminating bugs at the source through strict mathematical proofs, instead of patching vulnerabilities later. Building an operating system from scratch physically enabled a system with a 30% lower memory footprint than the legacy Linux platforms it replaced. When we zoom out from the microscopic architecture, a stark geopolitical reality emerges. The global computing supply chain has formally and likely permanently fractured into 2 completely incompatible systems. The international trade sanctions designed to freeze the specific technological progress acted as the exact catalyst that forced Huawei to achieve absolute technological sovereignty. If you want uncompromising, systems-level histories that prioritize real engineering mechanics over superficial daily news, make sure you're subscribed to the channel. The sheer difficulty of decoupling a supply chain always traces back to the physical limits of extreme ultraviolet light. To understand exactly how ASML built the monopoly that triggered this entire fracture, click the video on your screen now.